In this lecture, let us continue our discussion on the technique of scanning transmission electron microscopy. I'll just continue from where we left off in the previous lecture. I'll show you one of the very first designs of the STEM microscope, which was configured quite some time ago. In fact, the very first technique of rastering the electron beam and scanning to produce images was developed in as early as 1938 by von Arden, and also after that the technique didn't progress much. In late 1960s, Albert Crew actually started developing these techniques more with the advent of the field emission gun microscope. So if you look at the configuration of a STEM instrument, here is how it looks like. This is a slightly more elaborate version than the ray diagram that we saw in the previous lectures. So the idea is you have a kind of a dipole or a deflection coil, and with this, once you form a probe from the field emission gun, ideally with the field emission gun you get the best possible resolution. So you can use the dipole to actually deflect the beam, and you scan the beam in x and y directions to raster, and you can let this stay at different positions on the specimen, and you are simultaneously collecting the forward scattered electron signal. So you have either the bright field signal, which can be recorded. In old school days it was displayed on a CRT monitor, or you get the dark field signal, and with newer CMOS and faster detectors, direct electron detectors that are there, you can record very high frame rates and you can collect the entire forward scattered signal as well. From the construction of the old day detectors, you had these sort of annular dark field and bright field detectors in which the signal was separated, but now you can collect the entire forward scattered signal, and by using kind of a virtual aperture you can start reconstructing either a bright field or a dark field image from the same signal that is collected. So if you look at the photograph of the sort of first commercially developed FEG based STEM system, this was the system from Albert Crew. This is how the system looked like. These days there are modern dedicated aberration corrected STEMs in which the design is such that the electron gun is on the bottom and the detector is on the top, and this kind of gives much better stability, and you have exceptional energy resolution as well apart from spatial resolution. So the neon systems and also the test scan systems use this kind of design where the field emission gun is actually on the bottom, in contrast to the microscope designs that we saw thus far in this course where we were looking at the field emission gun being on the top. So there are these different variants as well that are available of electron microscopes. So don't go by the conventional picture that I tell you on the FEG being on the top and the scan coils below that and then the specimen. You can have it even upside down as well. So this is an overview of how the STEM instrument initially looked like. Modern day intermediate voltage electron microscopes all operate in both TEM mode and STEM mode. Depending on how you configure your instrument, you can have a host of all other detectors possible, and more recent developments, by recent I mean in the last 20 years, is the ability to collect even the secondary electrons as well from the specimen. So by placing a detector somewhere close to the specimen from the top, you can actually collect the secondary electrons as well, where you get a good surface sensitive signal also. You can simultaneously get STEM, bright field, annular dark field, high angle annular dark field, differential phase contrast image, and secondary electron image as well in modern microscopes. So the technique has evolved in leaps and bounds, and you get enormous amount of information from the same region within a specimen. So let us revisit the fundamentals of mass thickness contrast that we saw when we were discussing bright field TEM mode. So it is largely based on the Rutherford scattering. So the mass thickness contrast dominates the imaging in conventional STEMs. I have written scanning and transmission electron microscopes here. The origin is, it mainly arises from the atomic number, the thickness and the density. So that is why we do not separate them, you call it as the mass thickness contrast. And the regions with greater mass thickness scatter the electrons stronger and they have a difference in intensity. If I am recording it in bright field mode, greater mass thickness appears darker, but while I am imaging in dark field mode, the vice versa holds true. That is, greater mass and thickness would give you brighter image, brighter intensity in the image that you are recording. So the mass thickness contrast is governed by Rutherford elastic scattering expression. You have the probability of scattering, which is called as the scattering cross section, and the basic contrast relation can be written as, if I have contrast as C and delta I is the difference in the intensity versus I being the background intensity, the small thickness change or the mass change produces the contrast, and it is a function of this particular variable where there is an elastic scattering cross section. You can write it as sigma or you write it as q. The whole idea is, when I have a variation in the mass and the thickness, there is a change in the intensity and it is reflected in the image. So the physical dependencies that alter the mass thickness contrast, especially in STEM mode, are the scattering strength. If I go to the Rutherford scattering expression, it is somewhat proportional to the square of the atomic number. Higher the atomic number, the stronger the scattered intensity, the stronger the contrast is. If you have a lower accelerating voltage, the angles of scattering change significantly and you have a stronger interaction as well. You have greater thickness, that means you also have more scattering. When the electron intensity decreases exponentially with the mass thickness, the number of electrons that are deflected as a consequence of a scattering event can be modeled this way, where this is the Avogadro number of electrons that are scattering, and this contrast depends on the specimen variables, which are the atomic number, thickness and the microscope variables such as the collection angle, the brightness, the beam energy. So in practice the exact contrast calculations can be performed, but we rarely perform them. You use qualitative information when you are doing imaging in materials. In order to get a signal from STEM mode, the background electrons actually contribute to the noise. The image electrons, you should have a particular number. Typically, if you have a signal to noise ratio of 5, you consider it as good enough, because all these electrons, the scattered electrons, kind of follow the Poisson statistics. The fluctuation of the noise is somewhat equal to the square root of the number of electrons from the background, and according to Rose's criterion for visible image contrast, the useful image signal must be at least 5 times larger than the statistical noise. So imagine I have a specimen and I am kind of collecting the forward scattered electrons. You would always have some background noise, and the features that are contributing to my mass thickness contrast when I am recording the STEM image should be such that the number of electrons from these areas where it is strongly scattered should be at least 5 times over the, I am sorry, there is an error here, this has to be square root of capital N. So the signal should be at least 5 times larger than the statistical noise to be distinguishable in a TEM STEM image. So this means the contrast is such that I have a ratio somewhat inversely proportional to root over the noise here. So the principal parameters for STEM are as follows. The beam size is extremely important, because the beam size or the probe size is what ultimately determines the resolution. So the beam size, if I know the brightness written by capital B here, and if I is the flux of the electrons and alpha is the convergence angle, I can write it with an expression of this sort, where the current density can be measured like this, and the brightness here in terms of the solid angle can be measured from the beam current emanating from the tip of the emitter, and in terms of the solid angle from here I can compute the brightness value and use this here. And of course the solid angle is dependent on the semi-convergence angle through such a relation, and we know that the contrast here is effective signal over background, and typically this ratio should be greater than 5 to get a meaningful image. So considering all the aberrations that you have, so bear in mind, when I am forming a probe, in an ideal case, if I have the combination of condenser lenses which kind of form a probe, in an ideal scenario they should all intersect at a point, but with the lens aberrations this would definitely not intersect at a point, and there will be some broadening of the beam, and the beam diameter, due to all these other aberrations, you can call them as sort of an incoherent addition of the blurred probe, and the effective beam diameter can be measured as this value here, where you have the factors such as the spherical aberration, the chromatic aberration, and also the resolution limit and the brightness as well. So all these parameters together strongly influence my STEM resolution, and based on this I can just show you one of the schematic diagram from one of the earlier studies or the texts. As, let me erase this here. If I have a probe size d, it is strongly dependent on the brightness and the convergence angle, and you have an optimum value somewhere here which is a compromise among all of these. So depending on multiple parameters such as chromatic aberration, spherical aberration, the brightness and the convergence angles, you get an optimum probe size, and this is at an accelerating voltage of 20 kilovolt, and you would have a probe size of something around 3 nanometers. This is, I think if I am not wrong, for a thermionic emitter for a scanning electron microscope, but similar figures exist for a transmission electron microscope for a field emitter as well. You can achieve probe sizes as small as 0.16 angstrom as well. Of course you would have some beam broadening, and naturally this does not guarantee you the STEM resolution. People have successfully demonstrated that you can achieve 0.5 angstrom resolution, and even if I am not wrong, there are some modern literature which has been published which states they have achieved 0.3 angstrom resolution as well while imaging in STEM mode. There are of course picographic techniques with which you can achieve significantly improved resolution as well. So with all this, it is evident that STEM is a rastering technique. It critically depends on the kind of the source you are using. It also depends on how you are forming the probe, and the probe diameter is kind of controlling the resolution. And there is something that I would like to bring your attention to. When I talk about STEM as a different mode of imaging in TEM, it might be rather confusing or misleading on how is scanning transmission electron microscopy different from transmission electron microscopy. If you look at the concepts that were introduced in high resolution TEM, the ideas of projected potential, the parallel beams that are going through the specimen and satisfying the Bragg's diffraction and forming a sort of an interference pattern to get a high resolution TEM image. Similar ideas exist in STEM as well, but the only difference is the way the interaction volume is depicted slightly varies in STEM mode, whereas when I look at it in TEM mode, it is different. We saw the weak phase object approximation. The same kind of multi-slice approach to model HR TEM can also be used for HR-STEM as well. So let me try to relate the electron beam interaction with the specimen in TEM mode and STEM mode through something called as the reciprocity theorem. So if I look at how the specimen is illuminated in TEM mode versus STEM mode, the figure A that is shown here, I have taken this from the textbook from Tanaka. You can see that the specimen actually, when illuminated with a parallel beam, you have a parallel kind of an electron beam going through the specimen, and the exit wave now appears like a spot pattern at the back focal plane, and from these spots through an interference pattern you are constructing an image on the detector. Whereas in the STEM mode I am doing the converse or the opposite. I have a spot now which is incident on the specimen, and it is kind of diverging like a cone, and by collecting the summation of all these divergent electrons I am kind of constructing the image. So what this reciprocity theorem actually states is, I am primarily considering all the elastically scattered electrons, and if I swap the position of the source and the detector, I still obtain the same intensity. That means if I have from the source at a given brightness n number of electrons hitting my specimen, if it is in the STEM mode, they would only go in and deposit as a spot, and the cone that is forward scattered is constructed to form the image. Whereas in TEM mode I have a broad beam which is going through the specimen, and I am collecting the entire forward scattered electrons here. So I would effectively, if I integrate the whole thing, assuming there is no absorption and other kind of inelastic effects and largely elastically scattering effects only, the entire electrons should be sort of conserved. And if I swap the idea of a parallel beam going through a lens and forming a spot object at the back focal plane which then interferes to form an image, versus a spot from the specimen diverging and collected on a detector, and by area integration if I am forming the image, it is essentially the same, and the intensities and the entire interaction physics and the mechanism is exactly the same. The phase contrast that we saw in TEM mode in HR-TEM images, where the interference between the 2 or the 3 and the multiple spots that were formed at the back focal plane to form an interference pattern, is exactly the same kind of a mechanism in STEM mode, where if I assume there are small disks, overlapping disks, these would be kind of interfering with each other to produce the contrast even in HR-STEM images. So this is essentially called as the reciprocity theorem. So in TEM mode I have a wide parallel beam, the lens forms the image directly, the image formation in TEM mode is explained through wave interference and Fourier transforms, whereas in STEM mode I am using a tiny focused electron probe, I am rastering point by point across the sample, and I am recording a signal on the detector instead of forming a full image with lenses. So if I swap the positions of the source and the detector, the image intensity remains the same. This is the reciprocity theorem. And if I look at how the scattered electrons are collected on the detector and how the image is formed, I have this kind of an image. So this position very close to the optic axis, where I have this kind of the overlap between all these disks that are converging, this position is where I have the signal for the bright field image, and in these regions I have the signal for the dark field image. Depending on how large my collection angles are, I get different modes of imaging in STEM mode. Now if I want to understand how this image intensity, so if my exit wave here again is psi exit, for each position on these pixels I collect some signal like this, and I can do an area integral of whichever portion of this I am using to form an image, and I can actually get the construction of an image. So let us look at that mathematical formulation in the next slide. So when I consider the STEM image, it is a product of the scanned probe, the specimen interaction, which inherently consists of the projected potential, and integration on the detector. So when I write it in form of a function, it is a convolution of all these. So the projected potential or the exit wave from the probe is actually an integral, an area integral over the forward scattered electrons, and I can write this in terms of the frequency space as well, in terms of the frequency domain as well. And when I integrate this, I actually get an image which is an integral of this kind of an angular spectrum. And because I am scanning the probe laterally, if I say this capital R is the shift that is there in the reciprocal space, in terms of this vector, which is the scan coordinate, which is the position of the electron beam, from the difference between the probe that is actually on the specimen versus where it is deflected, I can generate the contrast by integrating this whole thing. And the contrast in STEM actually comes when I take the exit wave as a convolution between the forward scattered probe and the transmission function, and this depends on the atomic structure. So in STEM, when the probe position is moving, the deflection, if I account with a kind of a translation vector which is r minus r, capital R, the STEM image is obtained by collecting all these together, and the intensity is given by an area integral of the exit wave. So when I am collecting this information at small angles, I call it as bright field. This is typically less than 5, it is typically less than 5 to 10 milliradians. Large angles is called as the annular dark field, and the intermediate angle somewhere I have the annular bright field detector. So this is how I obtain contrast in STEM mode. So there is something else called as the Z contrast. When I am imaging in STEM mode with the higher annular dark field detector, by minimizing or eliminating the diffraction contrast, that is with large collection angles between 50 to 150 milliradians, the contrast or the area integral that I get, the intensity, is proportional to an exponent of z to the power 1.7, or people also write it as z to the power 2 minus x, and this exponent varies depending on which sort of a model you are looking at. There are lots of studies that have been done. There is work of Rodenberg, Pennycook, Peter Nellis, so many more studies, and there are many more. I am sorry if I have missed mentioning a few names here, but essentially the image intensity that you get is kind of proportional to z square, and in regular dark field STEM imaging, I get a dark background with my features appearing bright, and when I do high angle annular dark field imaging in HR STEM mode, specific positions of these atoms I can quantitatively actually measure from how many overlapping atoms am I getting this intensity as well, provided I know the thickness. So this is what you have in STEM mode, and with this I would like to draw a conclusion to this particular idea of STEM imaging.